All right. Welcome back, everyone, to ECE 590. Today, we have Xiaolongjiang presenting. Xiaolongjiang received his bachelor's and master's degrees in electrical engineering from the Zhang University of Science and Technology, China, in 2011 and 2014, respectively. He is currently working towards his PhD in electrical engineering at the University of Illinois, Urbana-Champaign. From August 2014 to July 2015, he was working as a research engineer in the Nanyang Technological University, Singapore. His research interests include design and control of electric machines and electrified transportation applications.
All right. Thank you, Max. I hope everyone can see my screen now.
Yep, you can see it.
Okay. Thank you for coming to join this seminar. And today I would like to talk about the modeling of harmonics and electromagnetic losses in a high frequency and a high specific power permanent magnet synchronous machines using drive pulse width modulation processes. So this is an outline. First, I will give an introduction about this application. Then I will talk about the equivalent circuit and losses modeling of the motor. Then I will talk about the drives part. So the equivalent circuit is a circuit for the motor. This study is a combination of the motor and the drive. So next, I will talk about the pulse width modulation processes and its voltage spectrum. Then I will combine these motor models and inverter models to predict the current harmonics. And then we will evaluate the electromagnetic losses using the modeling tools and different algorithms, which I will talk about very soon. So first, it's an introduction. So this application is really based at the aircraft electric propulsion applications. So NASA set these ambitious goals to achieve a very substantial noise reduction and emissions reduction, as well as fuel energy consumption reduction. So you can see from near term to mid-term to far term, these goals are very aggressive. So we propose to use electric propulsion, just like what we have been widely used in the ground vehicles, and apply those strategies to the flying airplanes. Another background information is that several studies have projected that electrified aircraft propulsion can help achieve the improvement goals I just listed, especially in a large aircraft. So this studies shows that some potential aircraft configurations, like Sugarvolt proposed by Boeing, Eve proposed by Rolls-Royce North America, HGTF proposed by United Technologies, now called Raytheon, and also two superconducting concepts proposed by NASA. So if you look at this figure of merit in machines, you can see the power is pretty high. It's in the megawatt level. and more especially, the specific power is quite high, up to 13 kilowatt per kilogram. And if you look at the current state of the art, the machine's specific power haven't been able to reach that goal. In today's aircraft propulsion motor, like this Siemens motor, it's 5 kilowatt per kilogram. For other applications, lower level applications like general purpose or electric vehicles, it's 0.2 and 2 kilowatt per kilogram. So it's an order of magnitude lower than the target of 13 kilowatt per kilogram. So we developed this motor for to meet NASA's ambitious goals at that high power level and a high specific power target. So this motor is an outer rotor motor with a self-driven fans as the cooling strategy. And the permanent magnets are held back arrays, so we can have a very strong magnetic field. And then we have air gap windings, so that the teeth is removed and a large portion of the iron losses can be removed as well. So this table shows several the key specifications of this motor. It's a 1 megawatt motor, rated speed 15,000 RPM. The number of poles is a very special one. It's 20 poles. It's a high pole count for this relatively high rotor speed. So these two parameter combined gives a very high fundamental frequency, which is 2500 hertz or 2.5 kilohertz. All right, another key parameter is this synchronous reactances here. It's 0.06 per unit. So it has a very low reactances or synchronous inductances. So what does that mean? So for power electronics drives, we have a limit on the switching frequency, right? So if we were gonna to drive the motor with a power electronics converter, the ratio between the switching frequency and the fundamental frequency might not be high. So typically we need to have at least 20 to make that ratio up to 20 to have a pretty good sinusoidal waveform. But let's say our fundamental is 2.5 kilohertz. If I need to have a 20 ratio of 20, then I need to have a switching frequency equal to 50 kilohertz. That's not easy for a 1 megawatt drive. So for low power drive, it's easy, but for 1 megawatt drive, that's not easy. So this ratio will be low, as well as this low inductance also makes the situation more challenging, because the harmonics divided by the reactance will be our harmonics voltage divided by the reactance will be my harmonics current. With this very small inductance, our harmonics current can be substantially high, way higher than in normal applications. In normal applications, we don't worry about this because the per unit reactance is around 1 or at least 0.5. So here it's 10 times lower. Why it is so low? Because First, we have high pole counts. The pole count, the reactance is inversely proportional to the pole counts. Another thing is we don't have iron teeth. So a large portion of the magnetic path is in the air instead of uh, ferromagnetic materials in conventional machines. So that's why this inductance is so low. So the challenge is the possibility of a very high harmonics current, distorted current, and that will trigger some potential issues such as higher losses and higher temperature rise in the motors. So we need to analyze this problem to prevent the motor from being not workable. So if the loss is too high, we cannot drive the motor with the inverter because the motor has a limited cooling capacity, right? So this is a drive system architecture. The motor typically has can be decoupled into two subsystems. One is mechanical, the other is electrical. And here we're going to just analyze the electrical system because we in this talk I'm particularly focused on the current harmonics. All right. So the electrical subsystem is a composed of some L like inductance and resistance component. And then this inverter is powered by a DC power source and then controlled by a microcontroller, which will send switching signals to the inverter and employing some pulse width modulation algorithms so that to modulate the DC voltage into a sinusoidal waveform, into actually 3 sinusoidal waveforms, so that we can power all 3 phases. All right. So we need to model the motor as well as the inverter. So first, let's talk about the motor. Okay, so normally the motor is represented by a serial connection of a resistance and inductance. And we can also have this divide the inductance into 2 components, which is leakage inductance and the magnetizing inductances. And here we add a another branch, which is called the rotor branch, because we not only care about the low frequency case, the fundamental frequency. We also care about the high order, the motor behavior at high order harmonics induced by the inverter. And those high frequency currents is asynchronous to the rotor, which means they will induce eddy currents in the permanent magnets, which is a very good conductive material. So in that part, it's like the slip currents or transient currents in the synchronous motors, in the traditional wind field synchronous motors. So this is our equivalent circuit, particularly for the high frequency case, both low frequency and high frequency case. So it's higher fidelity than our conventional model. And you see this RR here. There is a term it's S is the slip. It's the frequency difference between the stator excitation and the rotor rotation. Okay, so on the right is the equivalent circuit we just developed, and on the left-hand side is the drive. So the drive is not a single sinusoid. It's a combination of multiple sinusoids, starting first order fundamental harmonic, which with an order of 1, the first order, and then there will be a second order, third order, fourth order, etc. So this circuit is this is just not just one circuit. For each particular frequency, we will have an equivalent circuit like this, but they have this general form. And LF and CF is the filter. Because of the low frequency, we will have to add a filter between the motor and between the inverter and the motor to filter out the high order harmonics. And then this is a motor. So how to solve this circuit? First, we need to determine all the parameters in this circuit, like all the inductances, resistance, and capacitance. So the filter are fixed parameters, right? Its inductor and capacitor are fixed parameters. But for the rotor branch, we just added this R and L are frequency dependent because of the skin effect in these components, eddy current skin effect. And then we need to obtain the voltage PWM spectrum of this source, right? And then we can solve this circuit at in the frequency domain. So we will first transform each harmonic into frequency domain and solve it. Then we get the voltage divided by the impedance. Then we got the current harmonic spectrum. And then we can use the current spectrum to reconstruct the current waveform. And we can also use that current spectrum to calculate the losses, different losses corresponding to that harmonics. These losses will include iron losses and copper losses, as well as permanent magnet eddy current losses. All right, so first I would like to talk about the circuit parameters and the frequency. So I mentioned that the circuit parameter of this motor will be frequency dependent due to the skin effects. So how do we determine, calculate, or obtain the exact value of that? Here I used the finite element methods. We can use similar experimental methods later, but here I just use finite element as to demonstrate the principle. So first we will set the whole rotor region to 0 permeability and stationary. And then we can calculate the leakage impedance by applying a 3-phase current excitation. Okay, then we can calculate the magnetizing inductances by setting the magnets to non-conductive components. The last critical step is to calculate the RR and LRL, which is by setting the rotor speed to 0 and a permanent magnet are modeled as conductive components without any BR, remnant flux density. So there should be no back EMF. Then we can apply a voltage from the terminal by sweep, and then some currents excitation will be excited in this circuit, and divided the voltage with the current, we will get a impedance. So that impedance is the rotor equivalent impedance corresponding to a particular frequency. If we sweep the frequency at which the excitation is applied, then we will have a curve which is the impedance versus the frequency. Then we can calculate the we will know RR and LRL at that for different frequencies. Okay, so this three curves shows how the equivalent circuit impedance changes with respect to the frequency. Basically, REQ, which is the real component of the equivalent impedance, will rise with the frequency, while the inductance will drop with the frequency. And the angle has a minimum point. Okay, so we got the equivalent impedance versus frequency relationship. Then we need to fit. We still don't get RR and LRL, right? So just by using the method is to use a least square fit regression to find the RR and LRL that best fits this the curves I just shown in the previous slide. We can use two models. We can assume that RR and LRL doesn't change with the frequency, or we can assume that they are frequency dependent, which I call complex model. And you can use absolute error least squares fit or percentage error least squares fit. And the objective is to make the equivalent circuit parameter equal to the simulated curve. So in the complex model, what I assume, how does the resistance and the inductance change with the frequency? So this is just a approximation. This is actually does not represent the 100% accurate case, because if you look at this model, you can see that the conductor, the magnet, which is the magnet here, you assume that it's surrounded by some magnetic conductive material, but in reality it is not, right? But this is just a approximation. So we have the skin depth here, then we have a reduced conductor height here. Then the resistance will be dependent on this reduced conductor height. Okay, right, and the inductance will also be dependent by this reduced conductor height, and the reduced conductor height is dependent on the skin depth, which is again dependent on the frequency. So these circuit parameters are eventually frequency dependent. So this graph shows the different fitting results. So you can see if I use a simplistic model, the error is larger. And if I use complex model, the error is slightly better. Okay, but it's not, the benefits is not very significant because I use absolute error least squares fit. So you can see that most of the error happens at the low frequency range. So if we use percentage error least squares fit, then the improvement is obvious. The residue norm reduced from 0.18 to 0.02. So we decided that the complex model is more suitable for the modeling because it has higher accuracy, and we will use this the circuit parameters determined by this model to determine the current harmonics. Then how to calculate the losses if we got the current harmonics, right? The copper losses is dependent determined by the Joule's law, right? I squared R, but the resistance is frequency dependent. So this is for the copper losses, and it has a similar form of the previous resistance formula, but this is for copper, and the previous one was for the permanent magnet circuit. This is a AC resistance formula. Okay, and then the iron losses will be calculated by this the so-called KL2 model. So the traditional iron loss model is have a KH and a KE, which are hysteresis loss factor and the eddy current loss factor, and they are a constant. But at high frequency, the iron core material behavior is quite different from in low frequencies, and experimental results have shown that these factors will be dependent on the flux density, so it's not a constant. So we propose to use this formula to determine KH and KE. Okay, so and the rotor losses will be calculated by the equivalent rotor circuit parameters, which we have been able to derive the exact values for that circuit components. Okay, so once we got this circuit parameters, we need to solve for the source. We need to determine the source of the circuit, which is the inverter output voltage. All right, so on this picture shows the inverter, traditional three-phase inverter with 6 switches, right? And this modulation is I think most people are familiar with. So you have a triangular carrier, and you have a sinusoidal modulation curve, and then comparing this carrier and the modulating the reference curve, you will get the switch on and off signals for different phases, A, B, and then this is VAB, which is the VAN minus VBN. Then you got a VAB, right? So, but there are different alternatives. For example, you can naturally sample the reference, or you can regularly sample the reference. naturally sampled means that basically you don't sample it, it's not digitally implemented. But most nowadays it's mostly regularly sampled because we use digital controllers. And then this carrier, it can be a triangle or it can be a sawtooth. Sawtooth means you have a ramp up and then you drop to 0 and then you ramp up again and then drop to 0. So the triangular, you have ramp up and then ramp down, right? And slope down, ramp up and then slope down. So there are different alternatives algorithms here, but most commonly we use is the regularly sampled reference symmetrical double edge carrier PWM or asymmetrical double edge carrier PWM, and the space vector modulation. Sinusoidal PWM has a lower DC bus utilization factor. So if we add a third harmonic, third order harmonics into the carrier reference, into the reference, if you look at the reference here, it's a perfect sinusoidal, right? But in space vector modulation, it's equivalent to adding a third order harmonic into this reference waveform, so that you can make like 15% higher voltage, output voltage from a certain DC bus. Okay, for then this analytical spectrum of different algorithms have been developed a long time ago by other scholars. So we just took it and develop an algorithm, a program to calculate the spectrum. So this shows one example for the regularly sampled reference and a symmetrical double edge carrier space vector method modulation. So this shows that the analytical way of predicting the voltage match very well with numerical simulations. It also matches the experimental waveforms, but I do not include here. So you can see that this is VAB by analytical, and this is VAB by numerical, or more specifically, Simulink simulation. So VBC, VBC, VCA, VCA. So basically, they match each other very well. So that we can trust the accuracy. Maybe we want to do a little bit of comparison between different modulation methods. So here we use an indicator called weighted THD, which is the harmonics voltage divided by their order. So this number will be similar to its harmonic current amplitude, right? Because V divided by X will be current, and X is proportional to omega times L. So omega, the frequency is proportional to the order of that harmonic. So we can see that basically the single edge, the sawtooth carrier is not very good. The weighted THD will be relatively higher than the other categories. For example, this is 8.4%. This is 9.6%, while the other double edge algorithms are around 4.6 or 4.8. right? And also, you can see the slide. There was some subtle difference between different algorithms, like the how this spectrums spread in the in the graph. So that will cause some difference in the current waveform and eventually the losses. Okay. Okay, so if you look at this let's go to this slide. So if you look at this slide here, if we analyze a voltage A, line to line voltage A, B, B, C, and CA, you would realize that it's not a balanced three-phase system. Like for the fundamental harmonic, it is balanced, but for higher order harmonics, it is not. So that means the harmonics field does not rotate synchronously with the rotor, and it's not a constant magnitude, right? So classical circuit method is to use a positive, negative, and a zero sequence analysis. So we will decompose the voltage into positive, negative, and the zero sequence, and then apply to the corresponding equivalent circuit, and then got the positive, negative, and zero sequence current, and then change the current back to ABC phase. This is shows the total transform process. And remember that because the rotor circuit is frequency dependent, that means the positive and negative sequence impedance will be different, corresponding to to each harmonic. Okay, so this one shows the analytical and the numerical motor phase current by solving the by divide the motor terminal voltage, or the inverter output voltage, by the motor equivalent circuit impedance. So the analytical and the numerical results match each other. Okay, so now we got the harmonics. And in this slide, we want to do some comparison, see what those current waveforms look like. We got the harmonics, then we can transform the harmonics back to an inverse Fourier transform to get the time domain waveforms, right? And here shows if my motor speed is rated speed, or 0.9 per unit, or 0.7 per unit. You can see that you will get different waveforms, but what's obvious is that the waveform is not sinusoidal at all. But for lower speed, you tend to get a better sinusoidal waveform. That's expected because if your rotor speed is lower, then your fundamental frequency is lower, then the ratio between switching frequency and the fundamental frequency will be higher, which is more advantageous scenario. So this is a regularly sampled reference symmetrical double edge carrier space vector method example. That's here. And what's interesting here is that at speed equal to 0.9 per unit, we see large harmonics. This is actually some of the high order harmonics resonate with the LC circuit resonant frequency. So some particular harmonic voltage just reside exactly at the the resonant frequency of the LC filter. So that makes this this waveform very distorted and unfavorable. So this picture shows the different algorithms, the current waveforms of different algorithms. You can see that basically the sinusoidal. So I did not label them, but the sequence is corresponding to this sequence here. All right. So 6, 7, 8 will be space vector, and 3, 4, 5 will be regularly sampled sinusoidal PWM carrier PWM, and 1, 2 will be naturally sampled PWM. Okay. So if we look at this, we can see that the space vector method tend to produce higher distortions, the last three, right? And the sinusoidal PWM, they have better waveforms. But as I mentioned, space vector has its own advantages. It produces a higher DC bus voltage utilization. So you kind of need to make some trade-off. So and then we can calculate the losses based on the harmonic currents and the loss modeling method I just mentioned. So for algorithms 1 to 8, we have these loss numbers. We can see that similarly for so this is the additional losses caused by the harmonics. We did not consider the DC power losses and the fundamental flux losses in the iron core. So this is only for the harmonic losses. We can see that this single edge space vector method has very high losses. So its single edge is not usable. And the sinusoidal PWM is good, has relatively lower losses. And the space vector method has higher losses, but they can go up to higher voltages. So eventually the total system design will need to consider what's more important and what's more what are the main constraints in your system. So some conclusions. In this presentation, I present the motor equivalent circuit and the losses modeling of this high specific power motor, and also how to determine the voltage spectrum in the pulse width modulation processes. And then with these two modeling methods, we can calculate the current harmonics and the electromagnetic losses. And we show that for different algorithms, we can have different current harmonics and losses. So they have their pros and cons. We need to perform more trade study on this to determine what algorithms to use. And the future work will include the change of the inverter structure. Maybe first some main design parameters like by varying the filter inductance and the capacitance, or by varying the switching frequency. So those trends can be foreseen. If you have a larger filter, you will have smoother, more sinusoidal currents. But if you have a higher switching frequency, you will have good waveforms as well. So that's all. Thank you. If there's any questions, I will be happy to answer.
Any questions? It doesn't seem like it. Well, thank you so much, Xiaolong.
Yep. Thank you for attending.
I think if we don't have anything else, that concludes today's seminar for ECE 590. Thank you everyone for attending, and thank you again, Xiaolong, for that presentation.
Thank you, Max.